Hi, it's Paul Anderson. I'm sure you're familiar with global warming, how increases in the amount of carbon dioxide is warming the planet, but you may not be familiar with global warming's evil twin, ocean acidification. The cause is the same, increases in the amount of carbon dioxide, but the mechanism is different. Let me show you a demonstration. This is regular distilled water, and I'm going to use a pH meter to measure the pH of regular H2O, and it's going to be right around 7. Now I'm going to take that same distilled water, we're going to put it in a bottle, and we're going to add carbon dioxide to it. We're using a soda stream machine to shoot carbon dioxide in it. It's now just carbonated water. We're going to put it in a glass, and we're going to measure the pH now. I want you to make a prediction of what you think the pH might be. You could even use your finger and point on the screen to where the pH scale is going to be. Let's see how you did. The pH is going to be 3.6. It's really acidic. Let me show you what's going on. So if we take carbon dioxide and water and mix them together, we get carbonic acid. Now that can quickly dissociate and form bicarbonate. What we're doing here is we're losing one of these hydrogen ions, and that can dissociate again and we can form carbonate. We're losing 2 of these hydrogen ions. Now, if we look at the definition for what pH is, pH, remember, is the negative log of the hydrogen ion concentration. What does that mean? The more of this H plus that we have in solution, the lower the pH is going to be, and it's going to be more acidic. If we add more carbon dioxide, more of it's going to move in, and we're going to have more of this hydrogen ion, and we're going to have a lower pH. Now, the levels of each of these can change. Each of these are reversible reactions, so depending on the amount of carbon dioxide, it can move towards the left or it can move towards the right. Why is this a big deal? Well, life exists in this water, and life is regulated by proteins, and proteins require a specific pH. So studies are showing that if we decrease the pH and make it more acidic, organisms are having a decrease in metabolism, and they can have a decrease in their immune response as well. Now, how much of a change in pH are we seeing? If we look at pre-industrial levels, the pH of the oceans was really basic, 8.25. Post-industrialization, it had changed to 8.14. Now, there are going to be regional differences you can see on this map right here. And you might say that's not much of a change in pH, 0.11, but remember this is a log scale. So that represents a 30% change in the pH. What's it going to look like in the future? Well, as we play those models out into the future, by 2100, it could be as low as 7.80. Now, this low pH is going to devastate ecosystems for a different reason. This last carbon compound of the 3 is carbonate. That combines with calcium to form calcium carbonate. That's what the shell is made up of. That's what the bulk of a coral reef is made up of. And as we change the pH, we can change the level of that carbonate. What determines the concentration of these 3? Well, it's going to be the temperature of the ocean water, the alkalinity, but also the pH. And so we can use a Jerome plot to figure out what's going to happen over time. These are log scales of the concentration of these 3 compounds. The green represents the amount of carbonic acid, the red line represents the amount of bicarbonate, and then the black line represents the amount of carbonate. Remember, that's important for shells. And so if we look at it at acidic levels, carbonic acid is going to dominate. At neutral levels, bicarbonate is going to dominate. And then at basic levels, those that we would find in the ocean, carbonate is going to dominate. But this blue area represents what's going to happen as we change the pH. And as we decrease the pH, you can see what's going on. The carbonate levels are going to drop off, and the bicarbonate levels are going to increase. That's because that free hydrogen is competing with the shellfish, really. The free hydrogen is competing with that calcium carbonate to form more bicarbonate. And so now shells can't make their shells. If we look at what could happen over time, this is a pteropod shell at 7.8 pH. It is literally going to dissolve. And so if we look at, for example, coral reefs, they're getting hit with a double whammy. We've got global warming. An increase in the temperature is going to cause them to bleach or kick out all of their algae. I'll talk about that in a different video. But this ocean acidification is going to take that carbonate, and so they can literally not build more of the coral reef. And so these 2 things work together. What's the good part of global warming and ocean acidification? If there is a silver lining, it's they both have the same cause. It's increases in the amount of carbon dioxide. If we can decrease the amount of carbon dioxide, we can cool off our planet, and we can also slow down this ocean acidification. I wanted to thank Rebecca Blake. She put this out as an idea of a video that I could make. I'm going to make a couple of videos based on this. If you would like to suggest a video, put it in the comments down below or send it to me on social media. That's ocean acidification, and I hope that was helpful.
Every living thing needs water to survive. It is one of our most precious resources. But although water covers 70% of the Earth's surface, less than 1% of it is fresh water we can drink. In fact, 1 in 9 people in the world has no access to safe drinking water at all. As the population grows, this will only get worse, so we need to be smart about the way we use and manage water, especially in hot, dry areas of the Middle East, like the Sultanate of Oman, which is 80% desert. Here, the Falaj networks are used to transport water from natural springs, but with so many people and such little rain, providing enough drinking water was a challenge. So they turned to the sea, using a process called desalination to remove the salt and make it clean enough to drink. Veolia built one of the largest desalination plants in the Sharqiya region of southern Oman. It uses seawater to provide 375,000 people with drinking water. It's also the largest beach well catchment in the world and will soon be producing more than 130,000 cubic meters of water per day, enough to fill 52 Olympic swimming pools. Let's see how it works. Seawater is extracted from 28 wells that are 80 meters deep. It's passed through sand to filter out large particles, such as pollen or dust. Then polished to remove any tiny particles like bacteria. Next, the salt is removed by reverse osmosis. Pressure is applied to the water, forcing it through 7,000 reverse osmosis membranes. As the pressurized seawater flows over the membrane surface, water molecules are forced through the membranes, leaving the salt molecules behind, separating the salty water from the fresh water. The reverse osmosis membranes are then enclosed into a fiberglass shell. The membranes are connected end to end and housed in vessels. As the pressured seawater enters the pressure vessel and flows across the membrane surface, the water molecules are forced into and through the membranes, leaving the salt molecules behind. The rejected salty water goes back into the ocean. Back in the plant, minerals like magnesium and calcium are added to the water, plus fluoride to help reduce tooth decay. Now the water is pure enough to drink. The water quality is checked every day in our laboratory. Water is a precious resource that we all need to conserve, and there are small things that you can do to make sure it's not wasted. Turn the tap off tightly to stop it dripping. Turn the water off while you brush your teeth or wash your hands. And take quick showers instead of baths. We're counting on you to make a difference.
The water of the oceans of the world is almost always in motion. Hardly ever interrupted, waves break at the coastlines, sometimes strong, sometimes weaker. There is an enormous energy potential that is available round the clock and free of charge. A potential that, if fully exploited, could satisfy 40% of the worldwide demand for power. This equals the output of 700 to 800 nuclear power stations. Foyt Hydro Wavegen is developing technologies to convert this inexhaustible energy into electric power without the emission of harmful greenhouse gases. The operating principle of this wave power station is as simple as it is ingenious. An enclosed chamber has an opening beneath sea level, which allows water to flow from the sea to the chamber and back. The water level in the chamber rises and falls with the rhythm of the waves, and air is forced forwards and backwards through the turbine, connected to an upper opening in the chamber. As it is compressed and decompressed, the airflow has sufficient power to drive the Wells turbine. It is a feature of the Wells turbine, named after its inventor, that it is driven in the same direction by both forward and reverse airflow through the turbine. Even relatively low wave motions keep the turbine moving and to generate energy. This is how easily energy can be generated with a wave power station, day and night, all year round, as long as there are waves. The world's first power station of this kind was put in service as early as November 2000 on the Scottish island of Islay and has been feeding power to the grid ever since. Voigt Hydro WaveGen is convinced of the commercial potential of wave energy. We are certain that our wave power stations can make a significant contribution to supplying the world with climate-friendly energy. Voigt. Engineered reliability.
Electricity is the lifeblood of modern civilization. Unfortunately, the conventional production of electricity from fossil fuels comes with a detrimental side effect: carbon dioxide emissions to the atmosphere. These emissions are causing atmospheric CO2 to rise, resulting in significant impacts on global climate and the environment. While a transition to non-CO2 emitting renewable electricity is well underway, fossil fuels are still projected to be the dominant source of electricity through 2050. This feature, combined with growth in electricity demand, means that a further 50% increase rather than a needed decrease in CO2 emissions will occur by mid-century, unless cost-effective ways of reducing CO2 emissions from fossil fuel use are found and deployed. The capture and underground storage of CO2 from power plants, termed CCS, has been extensively researched and is likely to be effective in reducing CO2 emissions at some scale. However, the expense of this process and the perceived risks of CO2 transport and underground storage have proven to be major roadblocks to large-scale deployment. The Planet Doctors offer a simpler, safer, and cheaper method of power plant CO2 mitigation that we call accelerated weathering of limestone, or ALL. It works by reacting power plant flue gas with seawater and limestone. This results in the spontaneous capture and conversion of the CO2 to dissolved calcium bicarbonate. ALL actually builds on existing power plant technology. Wet limestone scrubbing or seawater scrubbing are routinely used to remove another flue gas pollutant, sulfur dioxide. We have shown that ALL can remove as much as 97% of CO2 from a gas stream at ambient temperature and pressure, of which about 80% forms dissolved calcium bicarbonate. If this compound were added to the ocean, it would increase the already very significant natural concentration of this long-lived seawater constituent. This increase in ocean alkalinity should help counter the chemical and biological impacts of ongoing ocean acidification caused by our CO2 emissions. To conclude, the Planet Doctors believe that ALL can help to more rapidly and cost-effectively lower the climate impacts of the world's growing demand for electricity while also providing benefits to the ocean. To test these ideas, we seek partners and funding to conduct a pilot-scale demonstration of the technology at a coastal power plant. We ask for your support in this endeavor.